All right, this is a sneak preview lesson on parent graphs, connecting with equations and their graph. The first thing you have to understand about parent graphs is that they are the simplest you can write the equation and still get the graph you're talking about. For example, if I want to find the equation of a line, the simplest you could write is y equals x. Lines have locator points. They're called y-intercepts. We graph them first, and then we graph the slope to create the rest of the line. Pretty straightforward like you did before. No pun intended. Now, if we're going to play charades, try to participate with me right here. And what I need you to do is to have your arms out in straight lines like this. Okay, give it a try. Put your arms out in opposite directions. That's the charades for a line. Next, then we got parabolas. Parabolas are going to look like parabolas because you have x being squared. Whenever x is squared, you're going to have curved arms going up in both sides here, and then you get this shape motion like this. So put your arms in a field goal position like this, and you'll have the charades for a parabola. Again, the locator point for those is called a vertex. Next, we got cubics. Cubics are just like parabolas. However, when you cube a negative, it stays negative, and that's why the left-hand side flops down. So in this case right here, we call this the point of inflection, and that actually has your arms, one arm going up and one arm going down. Give it a try. Put one arm up, one arm down. All right, let's move on to the next one here. Hyperbolas. This is going to be, you got to have coordination for this one right here. This is called a hyperbola. It's a two-part graph. The right-hand side goes up, and the left-hand side goes down. You're also going to notice these have dotted lines in them. They are called asymptotes. Parts the graph gets close to but doesn't touch. And then there's this locator point in the middle called the center. We'll get more into that in our next lesson, but that's what it is called for the hyperbolas. Now, if you're going to try to charades this one, you got to have your right hand swoop up and your left hand swoop down. It's kind of like giving yourself a high five, but they miss. Your right hand goes up, left hand goes down. Give it a try. That actually takes coordination. It's kind of weird. All right, go to your next one. Exponentials. What makes an exponential is the x is in the exponent. Pretty straightforward, right? I didn't really point out the hyperbola, but the hyperbola is whenever you have x in the denominator of a fraction like this, okay? Going on to exponentials, these are like airplanes taking off. You've already spent a chapter on this also talking about percent increase and percent decrease. This locator point doesn't really have a special name, so we're just going to call it locator. And it also does have an asymptote. These are the only two graphs that have asymptotes in them, the dotted lines that the graph gets close to, but in this case doesn't touch. Now, in this case right here, if you're going to draw it, you're going to have your right hand sit out in front of you. Try putting your right hand out in front of you like this. Then have your left hand kind of swoop up to the right, and then that'll be your motion for an exponential graph when doing charades. All right, moving on to the next one. Absolute values. These have a V-shaped graph. These guys have a vertex just like a parabola, but these guys also want to look just like the line. You'll notice the equations are very similar, except this one's got bars around it. So whenever you see bars around the x, that's an absolute value graph equation. And what makes it different from the line is that when these y values are negative, we know these absolute value bars make them positive, so the part that's going down here negative gets reflected up here and makes it going up instead, and that's what creates this V-shaped graph around the locator point that we have. That's absolute values. Next, we also have square roots. Square roots are basically looking like a parabola curve, right? But they're on their side, and you only have just a little shot off to the right. So it always has some kind of point like this, and it goes off to the right. So if you think about like dabbing, you got a locator point right here, and it shoots off to the right, like your hand's going to do also. Give that a try. It's pretty straightforward. All right, and our second to last one here is our sleeping parabolas. They look just like square roots. And the reason why we call it a square root graph is because the square roots are around the x. But if you ever see a plus or minus a square root, we know we have the full sleeping parabola because it's a parabola that's on its side, lying down. This is a locator point called a vertex, okay? This vertex then gets moved as we do things as well. But what makes this unique is it takes two equations to make this graph, therefore making it not a function. Because if you draw a vertical line through it, it crosses it twice, which is not typical to what you call a function. All these other graphs we just talked about are called functions because if you draw a vertical line anywhere through these, they cross once. All right, and then our last one. Oh, sorry, the charades for that one is just your two curved arms off to the side showing that you have a parabola lying down. And our last one here is a circle. What makes this special is that it has both the x and the y getting squared. X and y being squared then creates a center dot, which we call the center. And this last number helps us decide what the radius is. In this case, it being a 1, the square root of 1 is the radius. In this case, it just is a 1. If I had a 4 here and I square root that, my radius would be a 2. If I had a 9 and I square root that, my radius would be a 3, and so on. There's more to this that we'll find out as we go further into this chapter, but that's what you're going to do with that one. And if you do a charades for this one, just put your circle over your head, and you've got your circle graph. So when we meet in class, I hope you guys can do the charades for all 9 of these graphs. And the next thing you might be wondering, though, is this going to get any harder? And the answer is yes, it will get a little harder. And that'd be part of it, just you asking the question, how do they move? Well, when you ask about how these things get moved or changed, there's numbers you can think of like the stretch factor, like you had in parabolas. When you put a number in front of any of these graphs, plus or minus, it's going to make the graph get stretched or compressed. Like in a line, it makes it steeper or flatter, depending on what you put in there. And same with parabolas, they get steeper on the side or flatter, depending on what the numbers that you're using. And the negative flips the graph over. That same thing happens in all these graphs, with the exception of the circle, for how the graph's going to get transformed in its shape. Okay. Next, you can also talk about where you want to locate this thing. If you take any of these x's, look at where the x's are, and then also you put a pair of parentheses around the x, and then put a number in there with it, the graph's going to shift opposite what you see, like you learned in the parabola chapter also. And lastly, if you put a number at the end of these equations, like a plus something or minus something at the end of the equation, we know the graph's going to shift up or down, just like you've seen in the past with parabolas as well. And that's basically it. So I hope you guys can see at least how these parent graphs look and how they're going to connect with the equations. And now we want you to try that out on the assignment that we have called PG3 Intro to Parent Graphs. Hopefully this video helps, and good luck starting your beginning of parent graphs chapter.